In this video, we're going to review some basic concepts associated with logs, starting with the definition of a logarithm. And you probably want to start with making sure you're comfortable with the meaning of what a logarithm is. I want you to notice that we have a log statement here, and its equivalent exponential statement right there. And you need to be comfortable going back and forth between the two in order to kind of get a handle on what's going on with logarithms. You can read the definition here for yourself, but you want to first think of a logarithm as an exponent. Okay, it's the exponent that this a right here has to be raised to in order to get that x. Okay, so first of all, just looking at the two forms, if we have log base 3 of 27 equals some value y, what we're saying here is that this whole quantity is an exponent, meaning that y is an exponent. So we have a base of 3, and then we have y, and that is going to equal 27. Okay. Now, sometimes the way students memorize this, or remember it to begin with, I should say, kind of a visual, they take this orange kind of curling arrow to remind themselves that they're starting with the base 3 right there, raising it to the y power, and it has to equal 27. All right. Either way you look at it, we're looking at an exponent on the base that gives us this value. So with that in mind, example 1, fill in the blank, we have y equals log base 4x. So in this case, 4 is the base, y is the exponent that we need to raise 4 up to in order to equal x. In part B, n raised to the a equals b. Well, here we have a log base n, because that's our base, and we want a result of b, and that's what the exponent would equal. So this is log form, this is exponential form. And again, you can think of starting at the base, raising it to the a power equals b, and that's exactly what you have here. All right, next one. The next one, we have an ln. ln is equivalent to saying log base e, like this. But we're never going to write log base e, we're always going to write ln. So if that's the case, and we're writing this in exponential form, we have e is the base, raised to the m power equals g. And so again, we're starting down here and coming around like that. All right. And lastly, we have this e to the z equals 7. Well, e is the base, so we have the ln, right? That's log base e. Log base e of 7 is equal to the exponent z. So there we have going back and forth between logarithmic form and exponential form. So in example 2, they want us to write each of the logarithms as an equivalent statement involving an exponent. So with this first one, again, if you want, you can do this. Start at the base, raise it to that power equaling this. So we end up with 6 squared equals 36. Same idea here. Start with the base, raise it to that power equals this. So we have 3 to the negative 3 power equals 1 over 27. And then part C, notice I wrote log base e, which we're not going to write. We're going to write ln x equals 4. But if we think about it, we're starting at the base, raising it to the 4th power equals x. So that's going to be e to the 4th equals x. In example 3, we're going to write each exponential statement as an equivalent statement involving a logarithm. So here we have a base of 2. So we're going to write log base 2. That gives us 16 if we raise 2 to the 4th power. And you can double check that by doing this again, right? If you want. Okay. The next one, we have e as the base, so we're going to say ln. The ln of x is equal to 3. This is the exponent that e has to be raised to give us that. And the next one, we have what? We have log base 4. And we want to get a result of 1 over 16, right? When we raise 4 to the negative 2 power. All right, continuing on, we want to evaluate each of these. So with this first one, I think it's best if we can start thinking of this as, oh, I need the exponent on 2, right? 2 to the what equals 8. And hopefully we immediately see that that's 3. It'd be nice to get to a point where we don't have to write this statement, right? But you can double check it. 2 to the 3rd power equals 8. Okay. Here we want to raise 3 to a certain power to get 1 over 9. Well, you know 1 over 9 is the same as 1 over 3 squared, which is the same as 3 to the negative 2 power. So that's what we have here. Part C looks scary at first, but realize what a logarithm is. This logarithm is saying this is the exponent that you would raise 3 to get 5. In other words, imagine 3 here, the result, right? This is the exponent that 3 would be raised to get 5, so the result is 5. Like that. Next, we have ln, which again is log base e. So they're saying, what exponent do we raise e up to get e to the 4th? And if you're thinking, well, it's straightforward, it's right there. You're right, it's just 4. Here we want e to what power? Because it's ln equals 1. Well, that's going to be 0. And then with this one, if you would like, you could rewrite this as ln of e to the 1/3, right? 1/3 is the same as a cube root. So what exponent do you put on e to get e to the 1/3? 1/3. And that's that. So hopefully you're starting to get used to logarithms being exponents that we raise the base to get that number there. All right. Now we're going to solve some log equations. So I don't think I mentioned this yet, but if you have a log without a number down here at all, it's log base 10. Okay, so basically what they're saying here is 10 to what power equals root 10? Well, that's going to be a half, right? Like that. Over here, they want to know what is the exponent, right? ln of e to the pi. What exponent on e gives you e to the pi? That's just x equals pi, right? Here we want to take our base of 4, right? You could do this one this way. You could do a lot of these this way, really. But 4 to the negative 2 power equals x. So x equals 1 over 16. Next one, again, we can start with the base, raise it to the 3rd power, and it has to equal this. So what are we going to get there? We're going to get 4 to the 3rd power equals 7x plus 1. I think 4 to the 3rd power is 64 equals 7x plus 1. If I subtract, we get 63 equals 7x, and then we'll end up with x equaling 9. Next one, we could rewrite this as ln e to the 1/4 power equals x. And so again, this is asking for the exponent on the base e that equals e to the 1/4, and that's going to be 1/4. If you want, you can, on this one, you can take the half base, raise it to the 2nd power, and it should equal that. So you're going to get 1/2 squared equals 3x plus 1. That's 1/4 is equal to 3x plus 1. If we subtract 1 from both sides, I think we get negative 3/4 is equal to 3x. So x equals, when we divide both sides by 3, negative 1/4. Like that. Next one, we're going to take our x base, raise it to the second power to get 25. Well, that becomes in exponential form, x squared equals 25. So x equals 5. Next one, we could rewrite this as log base 49 of 7 to the 1/3 power equals x. And so again, if we start at 49 and raise it to this power and get that result, we're going to get 49 to the x is equal to 7 to the 1/3. Now, you know 49 is the same as 7 squared, and that's being raised to the x power. My goal here is to get the same base, and I think we're going to be able to do that pretty easily like this. And then if you remember properties, or I should say rules or laws of exponents, you're going to multiply these guys. So you're going to get 7 to the 2x is equal to 7 to the 1/3. Now the only way you make these two sides equal to each other, because they have the same base or bases, you're going to have exponents equal to each other. And so you're going to get x is equal to 1/6. Next one. Now, with these, well, these next two and also the very last one, notice we have variables in the exponent. And whenever we have that, we are going to get those out of the exponent by taking the logarithm of each side. In this case, we're going to take the ln because ln and e work so well together. Here, they want to know the exponent on e that gives us e to the 3x. Well, that's just going to be 3x. And ln 10 is just a number. It's approximately 2.3-ish, this ln 10, but don't worry about that. We're just going to leave it ln 10. It's considered to be exact in that form, kind of like pi is exact in this form. So if we multiply both sides by 1/3, we get 1/3 ln 10, and that one is done. Same idea with the next one. We're going to take the ln of both sides. 2x plus 5 equals ln of 8. So on this side, they want the exponent that e has to be raised to, right, because it's ln. That gives us this thing. Well, that's just 2x plus 5. And that equals ln of 8. Subtracting 5 from both sides, we have negative 5 plus ln of 8. And then dividing by 2, I'm just going to write it with the negative 5 in front so it's really clear what's going on. We have a 2 there, and I guess I should have an x equals this. There it is. Now, really, when we're solving an equation involving logs, we have to double check that the solution really works. So for what I mean by that is if you go back to f, for example, if we plug in negative 1/4 there, we're going to get negative 3/4 plus 1, which would give us log base 1/2 of 1/4 equals 2. Notice this value in here is positive. We can only take logs of positive values. And if it were negative, then I would say there was no solution here. So on the next example, we might want to be a little careful with that. Let's see what happens here. So we're going to take 3, raise it to the second power to equal that. So 3 squared is 9, and that equals x squared plus 1. And now we're going to go ahead and subtract 1 from both sides, so we have this. And then if you notice, we can take x to be equal to plus or minus the square root of 8. Now, if we were to plug in, and here, let's simplify that a little bit. We can take a 2 out like this, right? Or 4 out, I should say, and it becomes a 2 on the outside. If we were to plug each of these in, we would square the result, and we would get positive 8 and then add 1. So I think we're good in this case. But keep in mind that whenever you're solving a log equation or equation involving logs, you've got to make sure that that directly substituting your final result back into the equation does indeed work and doesn't give you a negative inside the that you're taking the log of. Okay, let's see. Looking at part L, let's go ahead and get the 10 on its own. So I'm going to write 10 to the 2x minus 7 equals 3 over 8. Now we're going to take log base 10 of both sides. I'm just going to write log like this. The base is assumed, 3 over 8, like that. And this is asking for the exponent that 10, the base, right? There's a little invisible 10 down here that I'm not writing. This is the exponent that 10 is raised to get 10 to the 2x minus 7. So that's 2x minus 7, like that, equals log 3 over 8. And then taking that a little further, adding over the 7, first 2x equals log of 3 over 8 plus 7. And then divide everything by 2, so we have x equals log 3 over 8 plus 7 divided by 2. And we'll leave that one right there. Finally, we've got a few important logarithms. No matter what the base is, when you're taking a logarithm, base anything of 1, that has to be 0. Because no matter what a is to the 0 power equals 1. Similarly, no matter what the base is, to get itself, you have to raise that base to the first power. So log base a of a is 1. Here, what do we have to raise a to get a to the x? Just plain x. And on this one, you've got, this is the exponent that a has to be raised to in order to get x. That's the exponent that I just circled there, that a has to be raised to get x. And look, a is being raised to that exponent, so we just get plain x. So there's some basics with logarithms. These do come with practice. If you do enough of this and really get comfortable with the definition, then you're going to find that this stuff is doable, but it takes practice. So go ahead and do the next 2 pages of practice.